Hello and welcome to this online lecture. Today we're going to be covering material from Math 136 for your online Ivy Tech class for week 6. We're going to be covering sections 3.4 through 3.6, which covers the graphs of functions. My name is Patty Kokish, and if you have any questions, please feel free to type them in the box on the side, and then I will get to them at the end. So we're going to start with section 3.4, which is our library of functions and piecewise defined functions. So the first objective is to be able to graph the functions that are listed in the library of functions. So we're going to start with learning what a bunch of different graphs look like, and then these would be good candidates for putting on some kind of note cards, like a flashcard, something like that. So the first function that we're going to look at is the square root function. So we have f of x equals square root of x. So we want to go ahead and list the domain and the range, the intercepts, even, odd, or neither, increasing, decreasing, and if there are any absolute minimums or maximums. So if we look at this, the domain and the range are going to be the set of non-negative real numbers because we're not going to have negatives under our square roots, at least not yet. So the domain and the range are both going to be from 0 to infinity, and it's going to include 0. The x-intercept, that's what we get when we set y equal to 0, is just 0, and the y-intercept is also 0. The function is not either nor odd, not even or odd, sorry, and it is increasing from 0 to infinity. And it has an absolute minimum of 0 at 0, so right at the origin here. And it just looks like this right here. Okay, so this is what your square root function looks like. It's important that you know these, so I would suggest definitely memorizing it. Probably the easiest way to do it would be to go through maybe the study plan in my math lab and work through a bunch of problems. Another option would be to create flashcards where you have f of x equals square root of x on one side of the flashcard and the shape on the other. Okay, now let's say we want to graph the cube root function. So we want to determine if it's even, odd, or neither, and then state whether that means that f is symmetric with respect to the y-axis or the origin, or neither. Determine any intercepts that exist and then go ahead and graph. So in order to determine this, we replace x with negative x. So we have f of negative x, and when we do this, we have cube root of negative x, which is just negative cube root of x, which would be the same as the original except negative. So that means that it's going to be odd. Odd means that you have something that's symmetric with respect to the origin. So again, this is the one where you replace x with negative x, and then you figure out if it's the same as the original. If it is, then it's even. If it's the opposite of the original, meaning everything is negative from the original, then it's going to be odd. And if neither of those things are true, then it's not symmetric with respect to anything that we're interested in. Determine the intercepts, so that means that in order to find the y-intercept, we set x equal to 0. So cube root of 0 is just going to be 0. So that just indicates that the x and y-intercepts are both going to be at 0. So if we plug in some extra points, we see if we put x equals 0, we get y equals 0. So we write it as a coordinate 0, 0. If we pick like a fraction as a point, maybe like 1/8, when we take cube root of 8, we get 2, so we just get 1 over 2 as that point. So we picked this because it was a nice one. So 1/8, 1/2 is another point. If we pick 1, the cube root of 1 is just 1, so we have 1, 1 as a point. If we pick 2, we don't get a very nice number because the cube root of 2 is 1.26, but it's still fine to sketch a graph of that. And then if we pick x equals 8, we get 2 out for y because the cube root of 8 is just 2. So once we have some of these points, we can go ahead and sketch them. And if you notice, the ones that we picked were all these ones right here, which are in our first coordinate, or our first quadrant. Now, we already know that it's symmetric with respect to the origin. So if we know that we have all these points, what we can do is we can flip them across our y-axis and then across our x-axis, and we end up with this other half down here. So you don't need to pick negative points because we know exactly what they're going to look like based on the points that are already on our graph. So here's a list of the properties. Domain and range are the set of all real numbers because we can take cube root of negative numbers. The x-intercept and the y-intercept are both 0, so it goes to the origin. The graph is symmetric with respect to the origin, which means that the function is odd. The function is increasing everywhere, so it's increasing from negative infinity to infinity. And there aren't any local or absolute minimum or maximums because if you see here, it's just increasing everywhere. Minimums and maximums happen where we go from increasing to decreasing or decreasing to increasing. This is just increasing indefinitely. So there is no local or absolute maximum or minimums. All right, the next one that we want to look at is the absolute value function. So we want to determine whether f of x is even, odd, or neither. And then we want to state whether that means that it's symmetric with respect to the y-axis or the origin, determine any intercepts that it might have, and then go ahead and graph it. So again, so far we've learned, let me just scoot back for a minute, we have learned the square root function. So again, if you're looking to memorize these, which you probably should, you could put f of x equals square root of x on one side of a note card, this shape on the other. We also learned the cube root function. Let me just get past here, which looks like this. Okay, it looks a lot like the square root function, except it has a piece over in the third quadrant as well. And to our list, we're going to add the absolute value function now. So what we want to do is we want to replace x with negative x. So if we do that, f of negative x is going to be the absolute value of negative x. Now, if you think about absolute values, they're always positive. We don't care about the negative. So this is just absolute value of x, which is exactly the same as our original. Now, if it's the same as the original, when we take x and we substitute it with negative x, it means that the function is even, which means that we have something that is symmetric with respect to the y-axis. Now, if we want to determine our intercepts, again, we have some boring intercepts, just 0, 0. So if we plug 0 in for x, we get 0 out for y. So it goes through the origin. And then we want to go ahead and probably pick some extra points just so that we're able to see what our graph looks like. So if we plug 0 in for x, we get 0 out for y. Absolute value of 1 is just 1. Absolute value of 2 is just 2, and so on. So by picking our points, we ended up with this piece that's in our first quadrant right here. And then what we can do is we can use the information that we found about symmetry in order to sketch the rest. So we know that our function is even, which means it's symmetric with respect to the y-axis. So what we can do is we can take the piece that's in our first quadrant over here and flip it across our y-axis to end up with this piece over here. This one should be pretty easy to remember what it looks like. Absolute value looks like a V, value V, not too difficult to remember. And again, it goes through the origin here. So here are some properties. Domain is going to be the set of all real numbers. So if we look at our x values, we want to look from left to right for x values. So it goes all the way from negative infinity all the way up to infinity. The range, that means we're looking from bottom to the top. Okay, the smallest y value that we come across is 0, and the largest is infinity. So the range is going to be from 0 inclusive all the way up to infinity. Or you can write it in set builder notation, which is y such that y is greater than or equal to 0. X-intercept and y-intercepts are both just at 0, so the only intercept you would need to list is 0, 0. It's symmetric with respect to the y-axis, which also means that it's even. Those two things are the same. Now it's decreasing from negative infinity to 0, and then it starts to increase from 0 all the way up to infinity. And again, when we're talking about decreasing and increasing, we're talking about x values. So we're looking over here, it starts to decrease at negative infinity and continues to decrease all the way till we get to x equals 0, and then it turns into an increasing function. And then it does have an absolute minimum. The minimum value is 0, and it happens at x equals 0. So it happens at your origin right here. And that's just because we're going from decreasing to increasing that we have a minimum. Okay, constant function is pretty easy to remember. It's just f of x equals b, where b is some real number. So for example, we could have f of x equals 2, or f of x equals 100, or f of x equals negative 1,000. It doesn't matter. But this just looks like a horizontal line. The equation is just going to be f of x equals some number, and then it's always going to have a y-intercept at b. Identity function is just the equation f of x equals x, so you could also say this as y equals x, and it's basically just a line that creates a 45-degree angle with your x and your y axis here, and whatever you put in for x, that's what you get out for y. The square function, f of x equals x squared, I think you've probably seen this before. This is a parabola, okay? So if we plug in some points, if we plug 0 in, we get 0 squared, which is just 0. If we plug 1 in, 1 squared is just 1. 2 squared gives you 4. And then you can plug the negatives in as well. You'll still get positive answers out for y because you're squaring those numbers. Cube function looks something like this. This and the cube root function are two functions that students get confused a lot, so it's important that you remember these. The cube function, if you know what the square function looks like, this piece looks very, very similar to that, but then it's symmetric with respect to the origin, so it has a piece over here as well. You can always plug in points as well if you forget what it looks like to kind of see what your graph will look like. Square root function we already covered. That looks like this right here. It's increasing, it just has one piece. The domain and the range are all positive, all non-negative real numbers. And then this is the cube root function that I was saying students oftentimes get confused with the cube function. So the cube root function actually looks a lot like the square root function. It has this piece over here, but again, just like the cube function looks like the square function, it also has this piece over in the third quadrant here. Reciprocal function is an important one. This is one that students forget a lot of times, but it's f of x equals 1 over x, okay? And it looks like this right here. What you actually have is you have a dotted line right through your y-axis and a dotted line right through your x-axis. Those are called asymptotes, and we'll be talking about those a lot later in the class when we talk about more rational functions. Again, absolute value function. This one just looks like a V. It shouldn't be too difficult to remember. And the greatest integer function. So what this is it looks like this, where we have f of x equals int of x, where what that really is the greatest integer that's less than or equal to x. So if we pick -1 for x, the greatest integer that's less than or equal to -1 is just -1. If we pick -1/2 for x, the greatest integer that is less than or equal to -1/2 is still -1. And really, if we pick any number between -1 and 0, the answer is just going to be -1. Now, if we pick 0, the greatest integer that's less than or equal to 0 is just 0. If we pick 1/4, then the greatest integer that's less than or equal to 1/4 is still just 0. So if you pick any numbers between 0 and 1, not including 1, you're going to get 0 out for this greatest integer function. So it ends up looking kind of like this step here, where really what you have is any numbers between, let's say, -2 and -1, not including -1, are going to just be -2, and so on. Any numbers between -1 and 0, not including 0, are just going to have an answer of -1. And you'll see we have these open dots here because this includes all numbers up to 0 but not 0, all numbers up to -1 but not -1, and then the actual point for -1 is right here. Okay, now we want to learn how to graph the piecewise defined functions. I just want to kind of reiterate, all the ones that we just went through are also summarized in your ebook, so it's important that you memorize these somehow. We're going to be doing transformations with these graphs in a little bit, and it's really important that you know what these look like. So I would highly recommend that you put the functions on note cards, where you have the equation on one side and the graph on the other, and then just continue to sketch them until you have those memorized. You could also work through the study plan in my math lab in order to get extra practice with this, but it is important that you actually know those for your exam. Okay, so for the piecewise defined functions, these are a little different. They're not too difficult once you understand what they're actually doing, but they're a little bit hard to understand at first. So let's take a look at this one. We have a function f, which is defined as this right here. So f of x is equal to -x plus 1 if -1 is less than or equal to x, which is less than 1. F of x equals 2 if x equals 1, and f of x equals x squared if x is larger than 1. So what we have here is we have a function that's defined by three different things. Okay, so we have f of x equals either this, this, or this. And the one that we use depends on what our value for x is. Okay, so if you look here, we want to find f of 0, f of 1, and f of 2. So if you think about it, f of whatever we have in parentheses, that's what we're plugging in for x. So if we're trying to find f of 0, what that means is that we have some number, x, that's equal to 0. So 0 is not greater than 1, so we're not going to use this piece down here. 0 is not equal to 1, so we're not going to use this piece here. But 0 is between -1 and 1. So that means that we're going to use this first piece here. Excuse me, let me take a drink real quick. Okay, so since 0 is between -1 and 1, we're going to be using this top function right here. So that means that all I have to do is plug 0 in for x in this top function. So I have -0 plus 1. Well, -0 is just still 0. 0 plus 1 is just 1. So that means that f of 0 is just equal to 1. So the only tricky part about these is figuring out which piece of the function you're using. Once you know which piece you're using, that's going to be your answer. All right, if you want f of 1, okay, that means we're plugging x equals 1 into our equation. So what we need to do is we need to figure out which piece to use. So if you look at these three pieces here, you want to think about which one do I want to use when x is 1. And if you look at it, you want to use this middle one because that's the one that says if x equals 1. So no matter what, if x equals 1, then your y value is just going to be 2. So that's your answer down here. And then for this last one, f of 2, what you want to do again is look and see which piece you want to use. So if you look, you probably want to use this last piece here because 2 is greater than 1. So what you're going to do is you're going to take 2, that's your x value, and you're going to square it. And 2 squared just gives you 4. So again, with piecewise defined functions, you just need to decide which piece you're going to use based on what your x value is. And then you go ahead and substitute that x value into your equation right here, and that gives you your y value. Now, if you want to determine the domain, what you need to do is you need to look at the x values that we allow. So if you look, the smallest x value that we've kind of accounted for or allowed in here is -1, because we have x greater than or equal to -1. So our domain is going to start at -1. We've put a bracket there because -1 is included. And then x does not have an upper bound because this last piece right here is just defined for all values of x greater than 1. So that means we could have x equals 2 or x equals 2 million. It doesn't matter. So that goes all the way from -1 to infinity. Now if we want to actually graph it, what we need to do is need to graph it in pieces. Okay. So what you do is you just take it piece by piece. All right. So we're going to have from -1 to 1. So from -1 to 1, it's defined by this line right here because we have -x plus 1. Now, probably the easiest thing to do is actually plug in points. So if you pick -1, you get -1 plus 1, which gives you 2. So you have a point here. And if you pick 0, we already found that we get 1 out. So what we have is we have just a line here that goes right through here. We have an open circle at 1 right here because we have x less than 1 here, so it's not included. So we have an open circle there. Now if x equals 1, we get a y value of 2 out. So that means at 1, we need to put a point at 2. So we just have a singular dot just by itself right there. And then it turns into x squared if x is greater than 1. So what you'll see is this dotted line and then this continuing blue line, that's the graph of the function y equals x squared. And again, by the end of this section, you should have these memorized. Okay, now it's going to take you a little while to do that, but you will eventually have those memorized, so you would know what this graph looks like. And we know that f of x equals x squared if x is greater than 1. So that means that at 1 we have a circle because it's not defined there, but everywhere to the right of that, that's going to be part of our graph. So the actual graph consists of this blue line here, this black dot right here, and then this blue line here. And again, at these two lines we have open dots because they're not defined for x equals 1. The range, if we look at it, the smallest value for y, again, when we're looking at range, we're looking from bottom to top. And if you look, the smallest value of y that we come across is 0, but it's not included, so we're going to have a parenthesis there. And then there is no upper bound on our y values because this arrow just indicates that it's going up forever. So we just have from 0 all the way up to infinity. Okay, let's look at an application problem here. So in the summer of 2009, Duke Energy supplied electricity to residences of Ohio for a monthly customer charge of $4.50 plus 4.2345 cents per kilowatt hour for the first 1,000 kilowatt hours that were supplied in the month. After that, they were charged $5.3622, not $5, per kilowatt hour for all usage that was over the 1,000 kilowatt hours. So we want to answer a couple of questions and then create a model. So if we only used 300 kilowatt hours in a month, we could probably figure out how much we're going to pay by taking the $4.50 charge, because that's just automatic, and then multiplying the lower rate, the 4.2345 cents, by our 300 kilowatt hours, because we only pay the higher rate if we're over 1,000. So we just take that and we multiply by 300. Make sure you change this 4.2345 into cents. So we move the decimal 2 places to the left. And we get $17.20 if we do that. Now the charge for using 1,500 kilowatt hours, that means that we're going to pay our $4.50, and then we used over 1,000. So what's going to happen is we're going to be charged the 4.2345 cents for our first 1,000 kilowatt hours. So we take our rate, which was our cents here, and multiply by 1,000. And then the leftovers that we had 500 leftover kilowatt hours that we haven't paid for yet. And for those, we need to pay the higher rate. So we take our higher rate, which is $0.053622, and we multiply that by the additional number of kilowatt hours that we used, which was our 500 extra. And for that, we get $73.66. So if we want to actually write an equation, we're going to let x be the number of kilowatt hours that we used, because that's what it's going to depend on. Now, if 0 is less than or equal to x, which is less than or equal to 1,000, then all we have to do is multiply x by the 0.04345 and then add the $4.50. So if x is less than or equal to 1,000 and greater than or equal to 0, then we have a cost function that's defined just like this. 0.042345 times our number of kilowatt hours, and then add 450 on the end. However, what we have here is we have situations where you can have x greater than 1,000. So if that's the case, then the charge is going to be your lower rate for the first 1,000 kilowatt hours, and then you add the 450. And then what you have to do is you need to find how much over the 1,000 you are. So you take your total and you subtract 1,000, and then you multiply that by the higher rate, which is 0.053622. And we could make this look a little bit nicer. So again, we take our first 1,000 hours, multiply it by our lower rate, add our 450, and then onto that we add the excess of 1,000, which is going to be found by taking x minus 1,000. So for example, when we had 1,500, we took 1,500 minus 1,000, and we got 500 extra kilowatt hours, and then we multiply that by our new rate, our higher rate. So if we go ahead and distribute this through and add the 450, we get 46.845 plus 0.053622 times x minus 1,000. Then if we distribute this decimal here to the x and combine like terms, what we're really left with is 0.053622 times x minus 6.777. So if we put this all together, we have this equation here where we have if x is between 0 and 1,000, then you use this first piece. If x is greater than 1,000, then you use this second piece right here. And if you look at our graph, from 0 to 1,000, we have one line. And then it's kind of hard to tell, but this from 1,000 on is a slightly steeper line, okay? So this is not all just one straight line. From 0 to 1,000, we have one straight line, and then from 1,000 on, we have another straight line that has a slightly steeper slope because we're being charged a little bit more for every kilowatt hour. So this is an example of a piecewise defined function for an actual application problem. Okay, now section 3.5 talks about graphing techniques and transformations. This is very, very important because we revisit transformations at several points later in the course. So it's really important that you understand how to apply transformations to your base graphs so that you're able to continue to do this later. So what we're going to do is we're going to take all of our base graphs, which were from section 3.4. Those are the things like f of x equals x squared, x cubed, square root of x. So you have to know what those look like, and then we're going to shift them around, we're going to flip them, we're going to stretch and compress them. So the first thing we're going to start with is using vertical and horizontal shifts. So if we look at this right here, we have f of x equals x squared, and what we want to do is we want to obtain the graph g of x equals x squared plus 3. So what we do is we start with a table, and this is until you know the transformations, you can kind of do it this way. We start with a list of x values. They're chosen from -2 up to 2. And if you think about what x squared is going to look like, -2 squared is just going to give you 4, -1 squared is going to give you 1, 0 squared gives you 0, and so on. So we have these 5 points here. And then what we want to do is we want to add 3 to each of those y values. So we take -2 squared, that gives you 4, 4 plus 3 gives you 7, okay, and so on all the way down. So we have a new set of points here. So if we actually look what this visually does to our graph, this black graph shows the original, f of x equals x squared, okay, and this will be something that you're familiar with. And then the blue graph shows our new g of x graph, where we took our x squared graph and we just shifted it up by 3. Okay, so we took all of our y values and we added 3 to each of them. So if you actually look at that, it looks exactly like the same shape as this black graph, except it's just been moved up by 3. So whenever you're adding a number outside of here, that's going to vertically shift your graph either up or down. It would move it down if it were negative. So let's look at this one right here. We have f of x equals x squared and h of x equals x squared minus 4. So again, we pick some values. But hopefully what you're noticing is that all it's going to do, if it's after our function, is just move it up or down. So we have our original graph, f of x equals x squared, and we have our new graph, which takes this black graph right here and just shifts it down 4 units and maintains the exact same shape. So if you move this down 4 units, instead of going through 0, 0, it now goes through 0, -4. And we just have this exact same shape right here. Okay, so if a positive real number k is added to the output of a function y equals f of x, the graph of the new function, which would be y equals f of x plus k, is going to be the original graph but shifted vertically up. And then if you have the same thing except k is subtracted from the output of a function, then the graph is going to be shifted vertically down by k units. So if you have a number that's either added or subtracted to the output of your function, then that's going to either move it up or down. So I like to think of these as being outside of your functions. That moves it either up or down. Now, if we have something like this, we have f of x equals x squared again. So again, we know it looks like that U-shaped parabola. We want to obtain the graph g of x equals x minus 2 squared. So what we actually want to do is we're going to start learning this by just plugging points in. So if we pick -2 for x, -2 squared just gives you 4. But for g of x over here, -2 minus 2, we have to do that part first. So -2 minus 2 gives you -4. -4 squared gives you 16. So that one goes through -2, 16. If we plug 0 in for x, 0 squared is just 0. But if we plug it in for g of x over here, or not for g of x, but for x in the g of x function, we have 0 minus 2 squared, which is going to just be -2 squared, which gives you 4 as our output. If we plug x equals 2 in, into our original, we get 2 squared, which is just 4. Into this modified one, we have 2 minus 2 squared, which is going to be 0 squared, which just gives you 0. So if we look at the original graph, again, you should know this is your original, f of x equals x squared. What this does right here, if we have x minus 2 squared, is it actually shifts it to the right. So this is the one that I like to say is a little bit counterintuitive, because what you have here is you have minus 2, but it actually shifts it to the right, not the left, like you might think. So when you have shifts that are outside of your function, like we did in the last couple of slides, that moves it up or down. If it's actually inside of your function, though, then that's going to either move it left or right. If it's subtracted, then it moves it right. If it's added, then it moves it to the left. So if we look at kind of this summary right here, if the argument x of a function f is replaced by x minus h, where h is greater than 0, then the graph of the new function is going to be the original graph, but shifted to the right. And then if our argument of our function f is replaced by x plus h, then it's going to be shifted horizontally left. So we want to use the graph f of x equals x squared to obtain this graph right here. So all we have to do is, at this point, you should know what's going to move it left, right, up, or down. So this plus 4, it's inside of our function, so it's either going to move it left or right. And since we have a positive number, it's actually going to move it to the left. So what we do is we take our original graph, this black one right here, and we shift it over to the left by 4, and we end up with this new blue graph right here. Okay, we can also combine vertical and horizontal shifts. My suggestion to you when you're doing this is go ahead and write out the shifts that you're going to do first and then actually do them. So this minus 5, it's outside of our function, meaning that it's not included in the square piece. So that either moves it up or down. Now if you recall, if we have minus, it moves it down. So that's going to move it down 5. And then this plus 3 is inside of our function, so that either moves it left or right. Since it's plus 3, it actually moves it to the left 3. So what we do is we take our function, we've replaced x by x plus 3, so that means that it's moving it to the left 3, which we just talked about. So we take our original graph and we just scoot it over to the left 3. And then we just move it down 5, since 5 is subtracted. And we end up with this right here. So we've moved our graph from the origin, we've moved it left 3, down 5, and then we have our parabola shape just centered around this point right here. We can also graph functions that have compressions and stretches in them. So let's say we have f of x equals absolute value of x. Again, this is the one that looks like a v. And we want to obtain the graph of g of x equals 2 times absolute value of x. So if you think about this, if you plug negative 2 into your original, absolute value of negative 2 is just 2. If we plug negative 2 into our modified function, we have 2 times absolute value of negative 2, which is just going to be 4. So if you look at this, all of your y values have just been multiplied by a factor of 2. So for example, if we plug 1 in for x, absolute value of 1 is just 1. If we plug 1 in for x into our g of x equation, 2 times absolute value of 1 is just 2. So if we look at a graph of this, the black one again is our original. That's how it's always shown here. Y equals absolute value of x is going to be this original here. And then our new function is shown in blue. And that one has been kind of stretched out vertically. So if you imagine taking this black graph and stretching it vertically, you would end up with the blue one right here. The larger the coefficient, the skinnier your graph is going to get. Now we also have vertical compression. So if we have fractions, it's going to kind of do the opposite. So instead of making it skinnier, it makes it wider. So if you look at this right here, all of your y values have been cut in half instead of doubled. So when the right side of a function is multiplied by a positive number, the graph of the new function is obtained by multiplying each y coordinate by that number. It's going to be considered compressed if you have a fraction, so that's going to be something like this over on the right-hand side, and it's considered vertically stretched if you have some number that's larger than 1. The smaller the fraction, the more compressed it is. Okay, so if you have 1/16, for example, that means that you're dividing each number by 16. It's going to be really, really kind of shallow here. And the larger the number you have, if you have y equals 16 times your original, then that's going to be really, really skinny. Now, if the argument x of a function is multiplied by a positive number a, and the new function y equals f times a of x is obtained by multiplying each x coordinate by 1 over a. So this one, we have a horizontal compression if a is greater than 1, and a horizontal stretch if a is a fraction. So for example, let's say we have this right here. We have y equals f of x. This is given. It's a trigonometric curve here, and we want to find the graphs of y equals 2 times f of x and y equals f of 3x. So what we're going to do for this original one is we're going to take all of our y values and we're just going to multiply them by this factor right here, which is 2. So for example, we multiply 1 by 2 and we get pi over 2 and 2. So that's this point right here. For this one right here, we take 3 pi over 2, we leave it, but we multiply our y coordinate by 2, so negative 1 times 2 gives you negative 2. So what you end up with is a vertically stretched graph. And for this one, what we're going to be doing is we're going to be multiplying our x coordinates instead, or not multiplying, we're going to be dividing by 3. So if you look at this right here, if we take pi over 2 and divide that by 3, we get pi over 6, 1, okay. 5 pi over 2, divide that by 3, we get 5 pi over 6. And 3 pi over 2, if we divide that by 3, we just get pi over 2. So if you look at this one has been horizontally compressed. Okay, the last big piece of transformations is using reflections around the x and the y axis. So if we have this function right here, f of x equals negative x squared, if we plug in some values, again, this is what you want to do until you're comfortable with how to actually do the transformations. But if we try this, if we plug some values in for x, we know that when we square them, it's always going to be positive. So here's kind of our typical graph. But what's happened here is that all of our output values have a negative sign out front. So all we're going to do is take our y's and make them all negative. So if you look at the original here, y equals x squared, all we're doing is we're flipping around the x-axis. So if you have the negative out front, basically if y has been replaced with negative y, then we're flipping around your x-axis. So you're turning it upside down. So when the right side of the function is multiplied by negative 1, then the graph of the new function is said to be a reflection around the x-axis. So again, if the right-hand side is multiplied by negative 1, then you're going to reflect around x. Now, if x has been replaced with a negative x, which is this case right here, then you're going to flip around the y-axis instead. And this should say reflection about the y-axis, not x-axis up here. So when the graph of a function y equals f of x is known, the graph of a new function y equals f of negative x is going to be a reflection around y. So again, if you make the entire right-hand side negative, then you're going to be reflecting around x. If you replace x with a negative x, then you're reflecting around y. These are always a good idea to actually plug in some points and make sure that whatever you've done actually works. So here's a nice summary of the graphing techniques. You can find this in your textbook as well. If you're adding or subtracting a number outside of your function, then that's going to vertically either shift it up, which is if you have a positive number, or shift it down, which is if you have a negative number. Horizontal shifts are the ones that are a little bit counterintuitive. So if you have f of x plus h, it's going to move it to the left. If you have f of x minus h, it's going to move it to the right. Compressing or stretching, if you have y equals a times f of x, it's going to stretch it if a is some number larger than 1, and compress it if a is a fraction. And if you have y equals f of a of x, meaning that your x has been multiplied by some coefficient, then it's going to horizontally stretch it if a is a fraction, and horizontally compress it if a is some number larger than 1. So for those, you replace x by a times x. And then for our reflections, if the right-hand side has been made negative, then you reflect around the x-axis. If your x has been made negative, then you reflect around the y-axis, meaning that you replace all x's with negative x. So if we look at this right here, we have kind of an opposite example of the other ones that we've done, but we want to determine the function that's obtained from a series of transformations. So we're going to start with y equals absolute value of x, and we're going to start by shifting it left 2 units. So if we look at our original, it looks like this. Shifting it left 2 units means that we're going to replace x by x plus 2. So really what we have here is y equals absolute value of x plus 2, and that's shown kind of in this purpley pink color right here. We shifted up 3 units, which is shown in green, so we take our new function, which was our purpley function, and we add 3 to shift it up 3, and we end up with this green graph right here. And then we want to reflect it around the y-axis, which means that we take x and we replace it with a negative x. And if we do that, we have y equals absolute value of negative x plus 2 plus 3, and we end up with this red graph right here. Okay, now let's look at something like this. We have f of x equals 3 over x minus 2 plus 1. So what we want to do is we want to figure out what our base graph is. Now, the only one that we had with a fraction was this reciprocal function right here, where we had y equals 1 over x. So we're going to start with this base graph right here, which looks like this. 3 over x means that we're multiplying by a factor of 3, so we're vertically stretching our graph out. So what we're doing is we're taking all of our y values and we're multiplying them by 3, so it's vertically stretched. So it maintains kind of the same shape, except it's a little bit stretched out. And then what we're doing is we're replacing x by x minus 2. So this is kind of inside of our function. So that's going to move it to the right 2. Now I did mention that there are asymptotes here, okay, kind of a dotted line that would go through your y-axis and your x-axis. So that moves along with it. So what we do is we basically take our y-axis and we move our dotted line that would have been through it, we move it to the right 2. And then we keep the same shape going around. And then this plus 1 is going to actually move it up 1. So we take our graph that we had in step 3 and we just shift it up 1. Again, we have this asymptote or this dotted line that went through our x-axis. It's now been moved up 1, so it moves right along with it. And then the shape just stays the same relative to our dotted lines or our asymptotes. Okay, let's look at this one right here. We have f of x equals the square root of 1 minus x plus 2. So we're going to figure out what our base graph is, which in this case is just y equals square root of x, which looks like this blue graph right here. And then what we've done is we've replaced x with x plus 1. So that means we're going to move it to the left 1, because we have a plus 1 here. This is a positive 1. And then what we've done is we've replaced x with negative x, because x has a negative sign attached. So that means that we're taking our graph right here and we're flipping it across our y-axis since x was replaced with negative x. Now the important thing to remember is that negative x plus 1 can be rewritten as 1 minus x, which is just the same as what our original looks like. And then we have plus 2, which just moves it up 2. So we just take our new graph from step 3 and just shift everything up 2 units, and we end up with the graph that we're looking for. My suggestion with these is to always pick a few points and make sure that it works. Meaning I would create a kind of a t-table that has x values, figure out what your y is, and make sure that you've drawn something that matches. So for example, if I pick x equals 0, I have square root of 1 minus 0 plus 2. Square root of 1 is just 1. 1 plus 2 gives me 3, which is my point that I have right here, 0, 3. So I do the same thing with 1, make sure that I get 2 out. Same thing with negative 3, make sure that I get 4 out, just so that you make sure that you've drawn something that looks correct. You've done all of your shifting and compressing and stretching and flipping correctly. Okay, now section 3.6 is not a focus, but I just want to do one example here where we talk about mathematical models and building functions. So let's build and analyze a function here. So let's find the distance from the origin to a point on a graph. So we're going to let our point P equal xy, and it's going to be a point on the graph y equals x squared minus 1. What we want to do is we want to express the distance d from point P to the origin as a function of x. And then we're going to answer a couple of questions. So if we do this, we need to remember how to find distance, which is given by this formula here. And in our case, since we're interested in the distance to the origin, we just use 0, 0. And if we actually do this, distance from x is going to be given as x squared plus x squared plus x squared minus 1 squared, because really y squared is just going to be this right here is our y squared. So all we're doing is we're taking our y and we're substituting it with x squared minus 1 because that was our original graph. So really what we have here, when we go ahead and square the x squared minus 1, we would get x to the 4th minus 2x squared plus 1. And then we go ahead and simplify, and we're left with x to the 4th minus x squared plus 1, square root of that. That's going to be our distance. Now, if we want the distance if x equals 0, that means that we just plug 0 in for x. 0 to the 4th minus 0 squared plus 1 is just going to be square root of 1, which is just 1. If we plug 1 in, 1 to the 4th minus 1 squared plus 1 is just going to be square root of 1, which is just, again, 1. And if we plug in kind of this nasty square root of 2 over 2, what we have is we have square root of 2 over 2 to the 4th power minus square root of 2 over 2 squared plus 1. And then it's the square root of all of that. I would highly recommend using your calculator to help you with this. But it's important that you know how to do some of this. What you'll end up with is square root of 3 over 2, okay? Or you may have gotten square root of square root of the entire thing, 3 over 4, and then you would break that down so that you have square root of 3 over square root of 4, which is just square root of 3 over 2. So again, what you're doing is you're taking your original point P, okay, which is xy. It's going to be a point on the graph y equals x squared minus 1. And what we're doing is we're finding the distance to the origin. So we're just plugging 0, 0 in right here. And then all we're actually doing is we're replacing y with x squared minus 1, since y is equal to x squared minus 1. And then we square everything and combine like terms, and we're left with this right here. And then we use this information to solve the subsequent questions.